So that wish list has to be very long. Okay, so Dr. Varsha, the introductory slide, please.
Is it necessary for daily introduction?
What about that new one person who has come to watch you, Dr. Senthil? I don't want them to I want them to realize who's speaking with them. You see, they
No, just display them. Don't need to say.
No need to say. Well, silence is golden, but not always. and it is necessary to know that people who are so well educated, as well as they have achieved their career in research and teaching, are ready to come to their level and come down to their level of understanding, and they're ready to teach. You see, this gives one particular message that you should, I think personally, as you grow more and more in your own career, the more humble you should become. And and this is already proved by our webinar series, where all the teachers have agreed to take so many classes, teach them everything, all free. And so that's the message. So it's a pleasure for me to reintroduce Dr. Senthil. He's working as an assistant professor in the Department of Physics and Astrophysics, University of Delhi. After completing his PhD from Central University of Hyderabad in 2003 in experimental condensed matter physics, he went on to do several postdoctoral research works and joined this university in 2008. He has 15 years of research and teaching experience and has taught several courses such as quantum mechanics, advanced solid state theory, laser and spectroscopy, etc. He has started the experimental plasmonics group, and 5 PhD students have graduated on this group. This is the introduction also inspires the attendees to think of PhD in research in various fields that they have, so many candidates, and they are willing to make a career in physics. They should know what all possibilities are there for them. And so Dr. Senthil has more than 60 research publications in international journals and is one of the most cited researchers in the field of plasmonics. His name has been included in Marquis Who's Who in the World in 2014, 31st edition. Welcome, Dr. Senthil. I'm sure this inspires the students further. Please share your screen and deliver the talk.
Thank you for the nice introduction.
Welcome, sir.
Well, thank you.
Mr. Pawan, I request you to switch off your video, please. Mr. Pawan Kumar, please switch off your video.
Yeah.
Yes, it's visible. Yes.
Yeah. Yeah. Right. So the screen is visible, right?
Yes, yes, yes. Please continue. Thank you so much.
Okay, thank you. So good evening, everyone. Okay. So yesterday we have seen the Drude theory of metals, the basic assumptions of Drude theory, as well as the DC and AC electrical conductivity. Okay, so that's what we have seen. So just if anybody wants to have a recap, okay, these are I just go through the slides, the same slides as yesterday, just for a recap. Okay, so these are the basic assumptions of Drude theory. Free electrons are considered, and no interaction between two electrons. Okay, and the number density and the space available for each electrons. Okay, these are the some numbers of the number density and the space available for the electrons. And as we have seen, it's a free electron and independent electron approximation. Okay, and the relaxation time, the major one good and very important parameter of Drude's theory is this relaxation time or mean free time. Okay? So, and the thermal equilibrium with the temperature of the, even after collisions, the temperature remains constant. Thermal equilibrium is maintained, right? And DC electrical conductivity we have seen, the Ohm's law, and the another form of Ohm's law is J equal to sigma E, right? That's a more generic way of writing the Ohm's law, okay? And how to derive the AC and DC and AC electrical conductivity in a very simple classical theory, okay? So that's what we have seen yesterday. So if there are any queries in this one, you are free to ask anytime. Okay, so we will now continue for the next section in the topic, which is this dielectric Drude model for dielectric constant of metals. Okay, so as Drude model is valid, people started talking about Drude model. This one famous scientist Lawrence just refined the Drude model by considering, instead of a free electron gas, okay, he considered the free electron conduction electrons to be made of small oscillators, simple harmonic oscillators. Okay, and rest of the assumptions are same as Drude model. Only thing is the free electron gas is modified with simple harmonic oscillators. Okay, so they have each electron behaves as a simple harmonic oscillator. They oscillate around their mean position or equilibrium positions, the spring constant, right? So when you apply a external electric field, right, the force acting on each electron is given by this formula, right? Simple differential equation, which is force. Okay, force acting on by due to different parameters. Like one is local electric field due to the oscillating field of the electrons, and the damping force because the each free electrons are considered as spheres. Okay, so they resist the applied electric field. Okay, so that is what is this damping force. And as such, since each electron is a simple harmonic oscillator, so the spring constant comes into picture, right? And that's what is given by this simple equation. Okay, and this EL exponential hyper is the applied electric field. Okay, so now solving this simple force equation, okay, you and substituting for instead of V dV by dt, we substitute for current density, right? And if you substitute for current density, then this equation becomes like this. Okay, dJ by dt is plus gamma j is some factor into applied electric field, right? This gamma is the resistance offered by the simple harmonic oscillators in the given system, right? And this, am I doing this one or somebody is doing? Okay. So, so this is what, okay, until here we have seen yesterday, right? So the applied electric field and is represented by this simple planar wave equation, and similarly the current density, if you also write in the same form, then on simplifying the equation, okay, you will get a
Sir, are the notations by you, so many arrows just popped up on the presentation?
no, I am not doing anything.
Okay, so I
Is somebody
request
is
you,
doing, or
student,
I'm
if
not doing.
anyone is doing it, please stop as it is disturbing the lecture. Yeah, now it's gone. Sorry to interrupt, sir. Please continue.
No, it's still continuing. Okay, 1 minute. 1 minute. I see arrows coming on the screen.
Yes. I don't know who is doing that.
It's actually it's not intentional. Students don't know that they have clicked on the lower bottom where you can do this. So I advise all the attendees to get used to the Zoom platform, please. Please keep your fingers away from the share screen and annotations, reactions, and other boxes which are at the lower down. So there is a reaction thing, and then there is a chat, and then there is share screen. Please keep your hands away from it. Okay, I request you, otherwise you will not enjoy the lecture. Yeah, please, sir, please go ahead.
Yeah. So by substituting the simple planar equation, we'll get a equation for the current density, right? Which is again a complex quantity, as you can see, and the current density becomes a complex quantity, right? So this complex quantity is the dynamic AC electrical conductivity, right? So as you can see, current density is represented by a complex quantity multiplied by the applied electric field. So this complex quantity is, so the electrical conductivity becomes complex here, okay? So at very low frequencies, okay? This omega by gamma is, when very low frequency means omega by gamma is much less than 1. So this term can be neglected. So this corresponds to the current density becomes real. So this corresponds to, again, DC conductivity, right? But as the applied frequency, means applied field frequency increases, this becomes a complex part. So at lower frequencies, the DC electrical conductivity dominates. At higher frequencies, the AC electrical conductivity dominates. So that is what is the information we get from this relation of current density and electric field. Okay? At very high frequencies, when omega by gamma is very greater than 1, okay, then this becomes highly complex. Okay, so the applied force is very much resisted by the harmonic free electrons, okay, and they are out of phase. So this applied field cannot pass through the metals given system, right? So they are completely out of phase because the omega by gamma ratio is highly greater than 1, so it becomes complex. So the applied field cannot pass through the metal. Okay, so that is what is the information we get from this simple minded derivation of current density, right? And so still our aim is to find what is dielectric constant. Okay, so how to derive information about dielectric constant. Okay, that's what we are going to connect. This is just a recap of what is the electrical conductivity, right? As we have seen in the previous slide. So the conductivity as a function of frequency is given by this equation. Okay, this complex equation. And here, so as Drude model, we are considering only the free electrons. Okay, but is it only the free electrons are participating in this equation? Okay, no, that is where the disadvantage of Drude theory comes into picture. Okay, so not according to this complex, where is this complex quantity comes into picture? Okay, so when analyzing that, we found that both bound electrons, which are bound to the nuclei, as well as conduction electrons, right, the free electrons, can contribute to the sigma or the dielectric constant of the given metal, right? So the bound electrons also contribute to the dielectric constant of the given metal, and that's how we can define this quantity as dielectric constant. Okay, the effective dielectric constant of a given material is given by this equation. Okay, the last equation, where the bound electron, there is a small contribution from bound electron also. Even though it is small, it is nevertheless it's appreciable, and it gives you it only if you include the bound electron contribution, then you can match the theoretical and experimental data. Okay, that's the whole idea. Just with the free electron contribution only, the experimental data does not match with the theoretical data. Okay, so that's why the incorporation of the bound electrons becomes very important. Okay, so so the effective dielectric constant when you apply electric field is given by this equation by just solving the Maxwell's equations, right? So epsilon B is the bound electron contribution, and this is a free electron contribution or conduction electron contribution. Okay, so this is one of the, but nevertheless, this complex contribution which is given coming from the free electrons alone, that is valid. Okay, that is straight away coming from the Drude theory. Okay, but only this small contribution of the bound electrons, okay, that becomes appreciable at you increase the frequency of the applied fields. Okay, so that is the disadvantage of Drude theory, but nevertheless, still it is a valid theory. Okay, very classical theory. And okay, in summary, we can write this effective dielectric constant in this. Okay, we can separate the complex part and imaginary, means real part and imaginary part, and write them in format which is comfortable to us. So we write it like this, which when you separate the real and imaginary components, it can be written in this way: omega p square, which is called the plasma frequency. Okay, plasma frequency, which means the dielectric constant. What the dielectric constant is the measure of the polarization, strength of polarization in a given medium, metal here, right? So plasma frequency. What is the plasma frequency? What is plasma means? As you know, plasma is a fourth state of matter, right? So where the free electrons or negative charges are freely moving in a positive ion core, right? That is what is plasma. Okay, so the plasma frequency of a metal, right, is given by this equation. Simple. So even a simple classical theory like Drude theory predicts the plasma frequency. So what frequency the free electrons oscillate, right? That is what is given by the plasma frequency, which is given by the simple equation Ne square by epsilon naught m, which is the mass of the electron, right? Epsilon naught is the dielectric permittivity, right? And all are constants, right? So for a given metal, this plasma frequency is a characteristic of a given metal, right? So given plasma frequency numbers, whatever number, like it can go up to 10 electron volts for metals, okay? For different metals, depending on their electronic configuration, the plasma frequency can be up to of the order of 10 electron volts, okay? Whereas for semiconductors as well as insulators, the plasma frequency will be much lesser, like less than 1 electron volt. Okay, so that's just for comparison between conductors and insulators, or metals and insulators, right? So this plasma frequency is a characteristic of a particular metal, right? So it gives you the measure of what is a strength of both. It works in multiple ways, like what is the strength of the dielectric or measure of dielectric constant in a given metal, or how much the frequency the free electrons are oscillating, right? So it gives so that's why it's a characteristic of a given metal, right? For if you know the plasma frequency, you can define the characteristic of the given metal, right? That's it's like a standard constant for a given metal. Okay, so the dielectric constant at the visible is given by finally this equation. Okay, for a bound electron contribution, which is even though it is very weak or small, it is appreciable one, and there is a free electron contribution, okay, which is given by this equation in terms of plasma frequency, which is plasma frequency again is a characteristic of a given metal. How much it can, the definition can be multiple, right? It can give you the frequency with which the free electrons oscillate, or how much is the strength of measure dielectric constant polarization happens in the given metal, right? So that's what it gives you. Just okay, for the sake of completion, this is an experimental spectrum for the dielectric constant, real part and imaginary part of metal, aluminum metal, right? If you see that, this is the omega p is the plasma frequency of the aluminum metal, given metal. So here the only because of its electronic configuration, as mentioned here, right? It has a definite free electron, right? P orbital electron, sorry, P orbital. So and there are rest is bound electrons. So it has only contribution from like free electron. Maximum contribution, 99% of the contribution is from free electron. So the bound electron contribution is very minimal. So this effective dielectric constant equation can be simplified as say the bound electron contribution is very small. So we can take it as 1, okay, and the rest is all free electron contribution. And so this approximation agrees very well with the experimental data, okay. So but does it valid for all metal system? No. So for aluminum, okay, this is the case. There is since it has a very well defined p orbital as the free electron system, right? So it has only the free electron contribution is dominant, okay. But if you consider silver, okay, commonly known metal, okay, this is not the case, okay. There is because again it's because of its electronic configuration. You can take example for silver or gold or copper, right? So there definitely you can see the bound electron contribution also, again because of the electronic configuration. See, for silver it is, you see 4d10 and 5s1. So there is always a hybridization between this s and d orbitals. It's 4d and 5s orbitals, okay. The electron from 4d goes to 5s, right? So you cannot define which one acts as a free electron, right? The 5s is not a true, even though according to the configuration, 5s is the valence electron, but this 5s energy wise, it can hybridize with this 4d orbital. So the SD hybridization always takes same as in the case of gold also. Gold also 5d10 and 6s1 configuration, electronic configuration. So this 6s and 5d orbitals, right? They can hybridize always, okay. This electron can move here and d electron can move, go to s and 6x orbital, and like 6s orbital can come to this one, right? So that's always a hybridization effect is there. So that's why the bound electron contribution is again appreciable here in these cases, like gold or silver or copper, right? So again, it depends on the electronic arrangement or electronic configuration of the given system, right? So that's where the bound electron contribution becomes very important, okay. So that's why we cannot simply write, we cannot neglect the bound electron contribution. So here the bound electron means like because of this hybridization, so that's why it's called interband transition, like s and d orbitals, like there is a transition happens from 5d to 6s in the case of gold, and in the case of Ag 4d to 5s hybridization happens, right? So that's why the bound electron here, it is called as interband transition, okay. Interband transition happens, okay. And that's where the experimental data and the theoretical data does not match, okay. People were working on this one for quite long time, until 1960s, because as a Drude model happened in 1900, right? Until 1960, people could not understand why this one, this experimental dielectric constant or the plasma frequency doesn't match with the experimental data, exactly match with the, there is always some deviation from the theoretical data. So that after various studies, they found that this hybridization is the main issue, that interband transition happens, and they contribute to the like bound electron contribution, which is now called as interband transition effect. Okay, so they, once you incorporate that one, then the experimental data is satisfied. Okay, so okay, this is a paper which tells you the same SD hybridization happens, right? So this is the essence of, see, this is written in 1983, right? So that much time it took to understand actually the even simple metal, the behavior of electrons in simple metals like gold or silver, right? So and that is the effectiveness of, again, Drude theory as well, right? So with a simple addition to Drude theory, the experimental and theoretical data were matching. As you can see here, after incorporating the interband or bound electron contribution to the silver data, it matches. The experimental, the dots or arrows are the experimental one, and the line is the theoretical data. So and it matches. Okay, so that is what the effectiveness of Drude model. So that's why it's called modified Drude model once you incorporate this epsilon interband transitions. Okay, for AG, the epsilon infinity or epsilon interband transition is around 4, right? That's what is given. Experimentally they found out, and then this experimental data is satisfied. Okay, so that is okay. This is again you can call it as an advantage of or effectiveness of Drude theory. Okay, a simple classical theory even explains this hybridization effect. Okay, so that's again the hybridization effect you can study in atomic and molecular physics, right? Or we will see this in hybridization, how hybridization happens because of the electronic configuration and all those stuff. If time permits, I will do in the towards the end of this week, the optical properties of metals or materials, right? In that section, we will take up this one, hybridization, right? Well, how hybridization influences the optical properties of materials in general, right? That we will take it up as a separate one. But for the time being, this one, hybridization effect is a dominant factor in this one, okay? So, okay, this again, summary of this one. And dielectric constant of a free electron gas or metals in general, right? So you can write the dielectric constant as in terms of plasma frequency, right? Plasma frequency, which is again a characteristic for a given metal, right? Given the plasma frequency, you can tell the characters of a given material or given metal, right? That's the idea. And the relative dielectric constant is given by 1 minus omega p square by omega square, right? And okay, this is a famous diagram with plot, which is omega versus epsilon r, relative dielectric constant of medium, and the plot looks like this. It goes from negative to positive. So I think in any solid state physics book, you will see this one, see this plot, right? So this simple plot tells you many most information about the metal. Okay, so just as you know, metals reflect light, right? So that's a high school definition. Metals reflect light, right? That's what you are seeing in silver plates reflect light, right? So how much light it absorbs or how much light it reflects. Okay, that's how much light it absorbs and how much light it reflects. Okay, so that's a simple question. So if, as a science student, if somebody asks you how much light yes, metal or silver plate absorbs or reflects, okay, so that the answer is from this equation. Suppose if omega p is less than omega, less than the applied electric field, right? So what happens if omega is less than omega p? What happens? As you can see, if omega is equal to omega p, right? This equation is 0. That's why this omega p is marked in this x-axis, right? Which is 0, right? So what happens at this when omega is equal to omega p? Okay, which means maximum absorption happens. Okay, all the light which is with the energy or frequency corresponding to omega p, the plasma frequency, gets absorbed, right? That's the idea. So now what happens less than omega p and above omega p? Okay, when omega is greater than omega p, much greater than omega p, right? The system doesn't interact with care about the higher energy one. So just it passes through the metal, right? The higher energy ones just pass through that. That is above omega p, right? So that's why it's positive, right? And lower ones, okay, the frequencies or energies which are much lower than plasma frequency. So nearby ones, okay, will get something will get absorbed and something will get reflected, but very low ones, right? Or when the energy is very low, right? Or when omega is much less than omega p, right? It cannot pass through because omega p is so high, right? So it cannot pass through the medium, so it gets reflected. Okay, so all the lights with the energy less than omega p will be reflected back. Okay, so that is what is the that is what is the definition of plasma frequency, right, in a given metal. So once you know that, less than those energies, less than plasma frequency will be reflected. Higher will be anyway transmitted, pass through the metal, right? So that is what is the information given from this equation. Okay, so this is even though it looks a very simple classical equation, it tells you anything and everything about the material or metal, right? Given metal. So that's why this equation is very important. Okay, right from the basic to the application points, research and application points. This is a very standard equation. Okay, so and okay, this graph is these are the information you can available in this graph, like what happens at omega p, right? All the light of energies omega p gets absorbed into the metal, right? And above omega p just transmits. Below omega p it gets reflected. Okay, that's why metals shine light, right? Metals reflect light. That's why. So this equation, simple definition of this equation is metals reflect light. That you can see it directly. So this is a mathematical way of writing metals reflect light. Okay, so this is the information you can get it from this equation. So okay, so any questions till now?
No, sir, not yet.
Okay, so everything is clear. Okay. Okay, so I will just instead of going into the details of this one, okay, I will just summarize in one slide. Okay, this we will see, this slide we will see in detail once I finish the rest of the things, okay, which I plan. But just for the check, since we have talked about plasma frequencies, so I just put a very comprehensive slide, right? If you metal, you can say any metal like aluminum, silver, or gold, right? Gold is in gold ornaments, right, which are yellow in color, right, which is a bulk gold, right? What is bulk gold? Do you means the particle size in bulk gold is in the micron range. Okay, so that's why you call it as bulk, right? And bulk gold, as you know, everybody knows that it's yellow in color, right? So why it is yellow in color? Again, you can tell from this plasma frequency, right? It absorbs certain light, certain energy of light, which is corresponding to the plasma frequency, and reflects. So it absorbs certain energy corresponding to omega p and reflects all other lights, right? So it absorbs some light and reflects. So the whatever the reflected energy is that, so that's why it's sorry, gold looks yellow in color and silver looks grayish in color, right? It absorbs that energy and reflects the relative energy associated with that. So it cannot so whatever it absorbs, it cannot reflect, right? So that's why whatever you see, gold is yellow in color. That's what you see, whatever it reflects. Okay, so that is what is summarized by this equation. So the plasma, why it is called plasmons? It is like in synonymous with electrons, right? We want to define the plasma. Yeah. But plasma, when you say it is fourth state of matter, it is only possible at very high temperatures. Okay, so that is what is the definition of plasma. So to differentiate from plasma, we call them as plasmons, and in synonym because they involve free electrons. So to be synonymous with electrons, it is called the plasmons. Okay, the plasmons means refers to the free electrons in the metal. Okay, so synonymous with electrons. Right? So that's why it's called plasmons. Okay, so in principle, okay, this another name is called poor man's plasma, right? Plasma, you can say. So, but plasma, when you say, you will get confused with the plasma which is available at high temperature. But this is at normal temperatures, normal room temperature. In every metal, these plasmons are available, right? So plasmons refers to the free electrons in the metals. Okay, and okay, this is what is the equation omega p, right? You have seen, we have derived that. So root of Ne square by m epsilon. As you can see, it's all are constants. N is the number density, right? So E is the charge mass, and dielectric permittivity of the vacuum, right? So it's a constant one. So it's a constant for a given metal. But okay, so this is one bulk metal, any given metal. This is a plasmon frequency, right? And there are okay, this is a very active area of research nowadays. Okay, nowadays you talk about nanoparticles, right? So you can make different size nanoparticles and different shape nanoparticles. So when you this first equation is for bulk gold, right? Gold or silver or any metal. But when you make the same bulk metal in the nano size range, right? Then this equation slightly gets modified in terms of 1/3 of this equation. Okay. So okay, this how it comes and all that we will see later. But for the time being, just remember that this is a difference between bulk plasmons and say nanoplasmons or localized plasmons. Okay, because in nanoparticles, the plasmons are localized on the surface of the metal nanoparticles, right? So that's why it's called localized plasmons. Okay? So the plasma frequency of that one is 1/3 of the bulk plasmons. And you can also have, nowadays you need thin films, right? You can make thin films of different material, metal, semiconductors or anything. So when you have a film of metal, right? So what is the plasma frequency, right? Again, when you have a film of metal, it
Sir, there is a question.
Yes,
Then
yes.
what is the upper arrow sign in third diagram?
Here
These
in this one, in this
blue
one.
arrow, yeah, in the third diagram. Yes, yes.
Okay. Okay. These are not errors. Okay. So these are okay. We say plasma. What is a plasma? Means when you apply an electric field to a metal, right? What happens when you apply an electric field? There is a charge separation happens, right? The electrons are affected by the applied electric field depending on their direction. So this plus minus corresponds to the positive core, which is the ionic core of the metal, and the negative charge corresponds to the free electrons, right? So when you have this arrow, big arrow, this one is the applied field, right? When you apply a electric field for this, suppose assume that this is a metal atom, right? Metal particle, right? And if you apply a electric field from bottom to up, right? Then as you know, as you apply electric field, the electrons move opposite to the direction of the electric field. So the free electrons goes opposite to the electric field. And when the free electrons are collected opposite to the electron field, the ionic core of the metal, right, goes in the opposite side. That's how they form a dipole, right? This is a dielectric. So how much they can separate, okay, that is what is the dielectric constant, strength of polarization, right? That's what you call it as dielectric constant. So this, when you apply an electric field to a metal, right, how much the charge separation happens, okay? So that's what this negative sign shows, that electron, this side is electrons, okay, and the positive sign is the ionic core of the metal, okay? So this is a charge separation. In all the figures, the plus refers to ionic core, right, and minus refers to the electronic charge, okay? Even in this is bulk, so it's a very distributed one, so that's why it is like a flat medium kind of thing. So here also, when you apply electric field, the electrons charge separation happens, okay, and the how much the charge separation happens, that is the dielectric constant of the given metal, okay, and how much this omega p is how much this free electrons oscillate, how much energy they oscillate, right? That's what is given by this omega p, frequency of the oscillation of the free electrons, okay? So these are not error bars, these are charge, okay, means negative charge and positive. Positive means the ionic core charges, and negative means electronic charges, okay? So this is so this explains both dielectric constant as well as plasma frequency. So both are interlinked. Whether once you talk about dielectric constant, automatically the this plasma frequency comes into picture, right? Or once you talk plasma in terms of plasma frequency, again the dielectric constant comes into picture, right? So this is a okay. The simple idea is when you apply electric field, okay, charge separation happens, okay, and that's what is represented as a simple figure, okay. The negative and means plus and minus charges refers to negative, minus charge refers to electronic charges, and plus charge refers to the ionic core, okay. So that is what, is it clear? Any other queries?
No, sir, I think not yet. Student, please reply. Yes, yeah, it is clear to him. Yeah.
Okay.
Yeah.
So these are not error bars. This, remember that these are charges. Okay, positive and negative charges. Okay. So this is okay. I just for the sake of completion, this slide is a hot topic in research. Okay, nowadays. So I'm not going into the details, but so this is just for the sake, since we have studied about this dielectric constant and plasma frequency, I just wanted to, for the sake of completion, I have put this one. Okay, if time permits, we can go into the details of this one later on. Okay, so not now, right now, no. Okay, so this is a summary of plasmons in metal. Okay, so even though this one, this actually predicted by the classical Drude model itself. Okay, so again, we are not talking, so remember that since we are using Drude model, we are not talking about any single free electron, okay? It's a collective oscillation. So the definition of plasmon itself is a collective oscillations, okay? We are not talking about any particular free electron, okay? In a given metal, it's a collective oscillations, okay? Of the free electron, all the free electrons. So this omega, that's why this omega b is a constant. It is not for only one free electron. No, it is for in a given system, given metal, for collectively, right? So the definition itself, collective oscillations of free electrons. Okay. So true to Drude theory, we are not talking about individual electrons in this case, individual free electrons. No, this in all the equations, this omega p corresponds to free electrons in total, right? Average frequency or energy of free electrons in total. Okay, just you have to remember that it is not energy or frequency of one single electron. Okay, so that is very, very important point you have to remember. It's always a collective oscillation. Okay, we are talking about free electrons in the whole metal. If you consider a metal, gold, silver, whatever metal medium you are considering, whole of that. Okay, and okay, this again, I will not go into the details of this one. This we will see later how plasmons propagate in a given medium. That's what. So okay. I was tempted to put this one, but right now I think it's not the time to. So this you can actually define in terms of how the antenna works, okay, or your optical fiber works, fiber cables, right? You can all do this one from this simple analogy using this plasmon and dielectric constant, but that becomes a separate topic itself. So we will not worry about how much distance you can pass the wave, okay, applied electric field without any loss. Okay, suppose if a electric field is passed through a wire, right, there is a resistance. You cannot keep on say if 1 kilometer long, can you send electric field through a wire? Okay, so when you send some energy here, after 1 kilometer, there will be a huge loss because there is through the wire, when electric field travels, there is a resistance, right? And damping of the electric field happens. So energy which you are giving at one end, after 1 kilometer or whatever distance, you will lose it, right? So now the area of the latest area of research is how to transfer energy without any loss, right? So these plasmons can be used for that. Okay, that's a overall idea, but how, that we will see later, right? That's beyond the scope of this work. So this is just to give you a idea of that one, but let us not worry about that for the time being. Okay. Now, so that's Drude theory predicts the dielectric constant of a metal, and so during the process of finding dielectric constant, we came across this plasmon frequency, right? So which is a standard for a given metal. So plasma frequency and dielectric constant are interrelated. Okay, if once you know about dielectric constant, you can talk about plasma frequency, or vice versa. Once you know plasma frequency, you can talk about the strength of dielectric constant and things like that, right? So now our next topic is how the wave is propagated. Means suppose if we apply a electromagnetic field to a metal, how much it propagates into the metal, right? How, like as plasma frequency, we have seen higher energies other than above plasma will be just transmitted, right? But lower energies will be partly absorbed and partly reflected. Okay, so what is how the electromagnetic waves propagate in the metals, right? So that's what we are going to see. So we just solve this simple Maxwell's equations. Okay, Maxwell's equations always give a solution to light matter interacts, how electric field interacts or electric or electromagnetic wave interacts with the medium, material medium. So these Maxwell's equations are the standard equations. Okay, as you know, okay, you have to. There is a good. There are many books available. You should read the biography of Maxwell. Okay, very interesting ones. You can read about that one. You just type in Google, you will get a lot of information about Maxwell, how he like put these four equations in perspective, right? In late in 1870s itself, right? So without any, his intuition is very exemplary, right? You cannot. That's why we are even now we are using this Maxwell's equations, right? Just whatever form he has given, we are straight away using it, and it works very well. Okay, whether it's a new material or a known material, right? It works. Okay, no material was discovered which defies these Maxwell's equations till now, right? So that is the interesting aspect of this Maxwell's equations. Okay, so okay, so this as you guys, okay, you might in this course you might have come across Maxwell's equations many a times, right? So just brush up your. These are the four standard equations with the rho charge density 0 when the. So these are the four standard Maxwell's equations, right? Now we solve for our case, we solve when an electromagnetic wave falls in the metal, what happens, right? How it propagates inside a metal. That's what we are going to see. So since we are considering electromagnetic, even though we are considering electromagnetic wave, the electric field is dominant, okay? So the effect of magnetic field can be neglected because as it is, the magnetic field is 4 times weaker than the electric field, right? Which you know, right? As you know, so the magnetic field component in the light is very weak, right? So because of obvious reasons as shown here, right? So the in normal way, when you say electromagnetic wave, you consider only the electric field part, right? Which is dominant. Nevertheless, there is a contribution from magnetic, even though it's very weak, but there is definitely a contribution from that. Okay, so that is again a hot topic of discussion. Okay, but for the time being, we assume that the magnetic field is magnetic component is weak, of light is weak, so we consider only the electric field component. Okay, so now again using the Maxwell's equation, the electric applied electric field, time varying electric field, this e power minus I omega t, right? We substitute in this Maxwell's equation. Okay, so we obtain a wave equation in terms of del square E, right? Which again directly gives you the complex dielectric constant, right? That's what we have seen before. Dielectric constant is a complex quantity, right? It can be differentiated in the real part and complex part, right? Which can be written in terms of this plasma frequency, right? Like 1 minus omega p square. Okay, this equation we have seen. So we will straight away get from this by solving this wave equation, right? But still further, okay, this is what we have seen till now, right? Now further by finding the current density, right? By applying the current density. In terms of current density, if you solve the same wave equation, right, you will get slightly more information. Okay, how much you will get the wave vector, right? How much distance the wave propagates inside the metal. Okay, the same equation in terms of when you write in terms of current density, same wave equation if you solve simply, right, by putting all the known parameters into the Maxwell's equations, right, you will get the wave vector, So that is what is given here in terms of again omega square, right? Dielectric constant or this what is that, conductivity, okay? Dynamic conductivity, AC electrical conductivity, right? As and there is a this equation is here. So C square is 1 by epsilon 0 and mu 0. So what do you understand by this equation? Okay, so this gives you actually the speed of light in vacuum, right? You can see, as you can see, epsilon naught permittivity and permeability in vacuum, right? The product of these two gives the speed of light, right? So again, this comes from Maxwell's equation. You can directly prove that from Maxwell's equation also, right? And that's how Maxwell proposed light as an electromagnetic wave consisting of electric field and magnetic field components. Okay, so this is the basic equation which tells that, which was again predicted by Maxwell. Okay, so we are again we are getting this equation again, or for instead of epsilon 0 and mu 0, we can substitute for what is that, c square, speed of light, right? We can direct this. So just remember this equation always. Okay, this was predicted by Maxwell. Okay, to show that light is an electromagnetic wave. Light consists of both electric field and magnetic field components. Okay, so that is what we are applying it here, and which tells you what is the wave vector, means how much this light propagates inside the metal, right? Something called what is that? Skin depth, right? Which means how much distance this applied electric field can propagate inside. Suppose if we have a 1 centimeter thick metal, right? And when you pass a light of some frequency, how much of this light penetrates into the given metal? Okay, so that is what is given by this wave vector equation. Okay, K equation, which is given by, okay, again this one, this equation, right? By just simply solving the Maxwell's equations. Okay, okay, the steps you can see from here. Okay, just solving the wave equation in terms of the current density and other known parameters, right? You will get this wave vector, and which will in turn gives you how much depth or how much distance the light propagates inside the material medium or inside the given metal. Okay, so for example, this copper, if you take what is in copper metal, when you pass light, right, how much distance the light can penetrate, right? It comes out around 0.66 micrometer. Okay, so 0.6 microns it can penetrate into the copper metal. Okay, so that is what is from the simple equation you can derive how much distance the light can penetrate into the given metal. So this is a very standard equation, right, with known parameters. So okay, if you are given the static conductivity and omega, what is omega? The applied electric field frequency, right? And c square and epsilon naught are constants, right? So when you substitute them, you will get a skin depth, right? Which is how much distance the light can pass through the material medium or a given metal, right? So that is what is given here. So solving just simple Maxwell's equations, okay, for a given material medium, it will tell you how much distance the light can penetrate into the given metal. Okay, and okay, again this one, what is the relation between dielectric constant and refractive index? Okay, So what do you mean by refractive index? Okay. What is the definition of refractive index? Okay. What is definition of refractive? Okay. You know that the refractive index is directly proportional to what? Directly proportional to, or from this equation you can see what is the relation between dielectric constant and refractive index. Okay, what is what do you understand between the relation between dielectric constant and the refractive index? Okay, so you write dielectric constant or refractive index in terms of dielectric constant and vice versa. So what is actually you define by refractive index? Okay, refractive index gives you the how much pure is your metal or how much pure your medium is, right? So refractive index in general refers to the purity of the medium. Suppose if it is a pure metal, right, either gold or silver, if it is pure, then the electrons, there are electrons and ionic core, right? So when you apply a external field, they just polarize, okay? The charge separation happens. So if it is a pure material, your theoretical values and experimental values matches. But see, in real, there are defects associated with the materials, right? So all materials are not pure enough. So the refractive index tells you how much is the purity of the given material, right? So that's what is the definition of refractive index. Okay, in general, refractive index gives you the purity of the given material. Okay, so that can be directly correlated with the dielectric constant. Okay, and
Sir, one student has asked for the localized surface plasmon resonance.
yeah. What is the question? What is the question?
Sir, they want to know about the localized surface plasmon resonance in nanomaterials.
Okay. So, okay, in bulk, if you see, okay, gold is you are making ornaments, it's in a solid form, right? In metal is in a solid form, right? So there you cannot differentiate each atom by atom or each particle, right? Because it's like they are bound, okay? They are bound to make a continuous solid. Whereas localized plasmon, when you say, the nanoparticles are generally made in solutions or colloids, they call, right? Suspensions in a solvent medium. Okay, so nanoparticles are made easily by in colloidal form or in solution form. So when you in solution, the advantage is that each gold atom or a particle, each gold particle means a collection of atoms, gold atoms or any metal atoms form a particle, right? So they are moving randomly in Brownian motion in a given solvent, right? Solution. So in general, the nanoparticles are quite stable in a solvent. That's what they are called colloids. Okay. So when so here each gold particle, unless in a bulk gold, which is a solid gold, where all the atoms or particles are bound together to form a solid shape, right? In colloids, they are in solution, right? So they are the particles of gold or any nanoparticle are freely, randomly moving with the Brownian motion. So now, but nevertheless, they are metal atoms or particles, right? So when you apply electric field, right, or when you pass light, plasma frequency, plasmons come with charge separation happens. So the charge separation happens. So how this charge separation happens in solution, where the particles are moving randomly, right? So each particle interacts with the light, right? So in each particle, there is a charge separation happens. Okay, when light falls on each particles, charge separation happen, negative charge and positive charge. Okay, so it is this happens in a solution. Suppose in a given solution, Avogadro number of atoms are there. So as many particles are there in the given solution. So each particle interacts with the light, applied light. So in each particle, there will be a charge separation happens. So that's why it's called localized. So each particle has its localized charge separation. Okay, so that's why it's called localized surface plasma, and it happens only on the surface. So that's why it's called surface plasma. It's plasma. So it's, since it happens only on the surface, it's called surface plasma, and it is local to each particle. So it's called localized surface plasma. Okay, so this happens when you make nanoparticles in solution or colloids, right? So that is so specifically it is called for nanoparticles in solution. It is called as localized surface plasma because each particle, the charge separation happens. Okay, is it clear enough?
Yes, sir.
Is
Yes,
there?
so yeah.
Yeah, it is clear, sir.
Yes. So nowadays nanoparticles, different nanoparticles are easily prepared in the colloidal mode or solution mode. Okay, so that's where this localized surface plasma in itself is a very hot topic in research nowadays. Research, so you can make not only different size nanoparticle, different shapes you can make, and you can see for different shapes how this localized charge separation happens in different your crystal structures, right? Different crystal planes, how the charge separation happens. That's what is the latest topic of research. Okay, so when you go to, if you are going for higher studies research, you will be okay in plasmonics field. That's what we do. Okay, so that we will talk in some other time, right? But right now, okay, this is about refractive index and relation between refractive index and dielectric constant or plasma frequency. Okay, so wherever you talk about dielectric constant, these parameters automatically comes into picture, whether you like it or not. These are just yeah, derivative or correlated phenomena. So like when you say dielectric constant, plasma frequency automatically comes into picture, and automatically the refractive index comes into picture. So all these are interrelated or correlated parameters. So that's why I put it them in order. Okay, I think I'm taking more time, right? So I will stop here. Okay, we can continue
Dr.
tomorrow.
Senthil, you can take long, it's not a problem. But as I said, the students after 3 hours, they just find it a little bit
Yes,
difficult
yes.
to grasp.
No,
And
next
that is
period.
understandable. That is understandable. So we limit to the time, and we
Yes.
have the pleasure of listening to you again tomorrow, day after, and so on.
Sure.
Thank
So
you
I
so
will
much.
stop
Thank you so much.
at this point.